hopefully this week, today and Tuesday, we'll finish chapter 2, where we're going to continue talking about random variables. Today, we're going to introduce a very important distribution or random variable. It's called the Gaussian or normal random variable. This distribution is very important, has several applications. For example, it's used heavily in statistics, communications, and other applications. So let's begin with the notes. Can you see the notes on the screen? Hello?
Dr. Rubain.
Okay. So, like I said, Gaussian is an important random variable. So, of course, a random variable x, it's called Gaussian if it has the PDF as shown in equation 1, as shown here, right here, where we have these important parameters. The first one is the mean or the average, and it's shown here, x minus m. And the second parameter is the standard deviation, sigma. And the third one is the variance, sigma squared. Okay, so if you see a PDF given in this form, okay, it means it's a Gaussian or normal distribution or normal random variable. Okay. Of course, we do not expect you to remember this PDF. We don't memorize PDFs. It may be the easy one, we can memorize them, but this one is not easy to memorize. Normally, if you have, normally they are given in the problems or the example or something, or you can refer to it in the book, where you can get the information from the PDF. This is the whole idea of giving the PDF, not to memorize it, okay, but to understand it and to understand the way how to find these three main parameters. Okay. Now, the Gaussian PDF is normally centered around around x, where x is equal m, around the average. Okay, as shown in Figure 1, as you can see here, and it's symmetric around m, around the average. Okay, and as you can see here in red, the area between m minus sigma and m plus sigma represents almost 68% of the area under this curve. Okay. Of course, some other statistics showing that when m minus 2 sigmas to m minus plus 2 sigmas here, like from here to here, present almost 95% of the area. So it means the top one is just above m plus 2 sigma and below m2 plus 2 sigma, the 5%, okay? Now, in special cases, when the average or the mean is equal 0 and sigma is equal 1, the standard deviation is equal 1, in this case, the random variable x is called standard normal random variable or standard Gaussian random variable. So if somebody would say, given a standard normal random variable, it means m is equal 0 and sigma is equal 1 without giving these numbers. Okay. Now we can use shorthand notation for Gaussian random. Okay, Gaussian random variable, as shown in equation 2, where the random variable x is distributed normally or Gaussian with mean is equal m and sigma is equal and sigma squared. Now, some books, instead of m, they use mu, as long as, it doesn't matter what they use, m or mu or whatever, as long as they define it as mean or average. Okay. So in this book, or in our notes here, we are using the average as m, okay, instead of mu. Okay. So if you have a problem and the problem says, given this notation, just like this, x and m sigma square, it means it's a random variable where m is equal, for example, 1 or 2, and sigma square is equal to number. So without saying this is Gaussian, you should know this notation means it's a Gaussian distribution or Gaussian random variable, okay? Now, the CDF of Gaussian random variable is given in equation 3, and which is basically the PDF given in equation 1, okay, right here, and integrated from minus infinity to x, where if you go back to the PDF, the last lecture, one of the properties to find the CDF is taking the PDF and integrated from minus infinity to x, and that's basically what the CDF of a Gaussian random variable. And at the bottom page, page 38, we have two examples where we are plotting the PDF here. The first one, we are given the standard normal distribution where sigma is equal 1. In this case, obviously, sigma squared is equal 1, and m is equal 0. So when you plot it, it's going to be plotted almost something like this, as shown in figure 2. And the peakedness will be 0.4. So if you go back to equation 1, the PDF, and plug in m and sigma, or sigma squared, and x is equal 0, it's going to be equal 0.4. Similarly, figure 3, yet this is another example. We have the normal distribution where m is equal 3 and 4 is equal sigma squared. And also in this case, when you plug in the numbers and x is equal 3, the peakedness here is going to be 0.2. Okay, you can try it yourself at home and verify that yourself as an exercise. Okay. Now the CDF given in equation 3, as you can see, is not easy to deal with. So normally we use software programs or tables readily available for this. Okay, but we can't use it as is. We have to convert it to commonly used standard forms like error function, as shown in equation 4, or complementary error function, which is 1 minus error function, minus the 1 minus the error function, as shown in equation 5, and also phi function and q function. And we're gonna in this lecture or this semester, we're gonna focus on the phi function and the q function, and the mathematical definition for these functions are given in equation 6 and equation 7, as you can see on the screen right here. Now, phi, which is right here, equation 6, it's really basically the CDF or fx. Okay, so if I know the mean and I know the standard deviation, I can find the CDF in terms of phi function. Okay, and then once I have this information, okay, I can go to the tables for phi. Okay, they are readily available, calculated. I think we have some in our book. If not, you can find it on e-learning. You can find it on the web easily, and also you can represent it in Q function. So we do have both. We have tables for phi and we have tables for Q, where phi is equal 1 minus Q, and of course Q is equal 1 minus phi. Okay. So this is what we're going to focus on today. So in terms of probability, if we are given a distribution, okay, as you can see here, and we are given a normal distribution where the mean is given and the standard deviation is given, or the variance is given right here, okay, we can find the probability of x larger than x, the probability of the random variable x larger than the value of x, and also the probability of x less than small x. Now, equation 11 right here, if you go back to the lecture before last, this is a definition for the fx or the CDF. So equation 11 and equation 8 are the same. Equation 11 and equation 8 are the same because this is really the fx or the CDF. And this one here this is basically equation 10. It's 1 minus fx. Now, if you go back to the properties of the CDF on what we discussed last lecture, or the lecture before actually, lecture before last, you will see equation 10 right here. It's 1 minus fx, which is 1 minus 5. Okay. Now, if we need to evaluate Q function with negative values, let's say if we are given a negative value, as you can see here, Q of x is equal 1 minus Q of minus x. In this case, if we have a negative value, okay, or the x is negative, so x minus the Q of minus x, basically it's 1 minus Q of x. As an example, a very small example, if we have Q minus 2 is equal 1 minus Q2. Of course, Q of 2, if you have the table, you can find it right away. It should be a number, okay? Okay, and you plug it 1 minus whatever the number is. And we will have an exercise in a minute about this one. Now let's go to page 40, where we have an example. In page 40 here, we have a random variable. And this random variable has a PDF, is given in equation 12. And if you compare equation 12 with equation 1, you will see it's, where's equation 1? Equation 1 on page 38. And it's the same form, general form, which means it's normal distribution or normal random variable, okay? So the equation 12 basically is a PDF for a normal random variable, okay? Now we can take a look at this, and from here we can see we need to find, of course, if you take a look at what's needed, we needed some probability. It means we need the mean and we need sigma, okay? So we are looking for two parameters. From here, from equation 12, we can define the mean. The mean is given here, x plus 2, which means which means m is equal minus 3. If you go back to equation 1 on page 38 and compare it, it's going to be the mean in this case is equal minus 3. And also from here, the square root of 8 pi is equal to 2 pi square, 2 pi sigma squared. So when we do the math, we all know how to do it. This is very straightforward. You will see that the variance, sigma squared is equal 4, and sigma equal 2. So we did find the parameters that we are looking for to find the probability. Sigma is equal to and minus 3. So if we do the first one, the probability of x less or equal to 0, okay? So you can find it in phi function in terms of phi or q function. Any way you want, it's fine. So if we decided to do it in q function, this one is the CDF, okay? So the CDF of x, the CDF of x is equal 0, okay? So in this case, where x is equal 0 minus m, x is equal 0 minus m divided by sigma. Of course, m is minus 3, as you can see here, and sigma is equal 2. So in this case, the solution for the first part, A, is equal 1 minus q 1.5 or 3 over 2. Similarly, we can, for part B, it's showing x, the probability of x larger than 4. And if you go back to the previous page right here, it's equal to the q of x minus m divided by sigma, equation 10. So we applied this right away. Okay, so x in this case would be 4, and m and sigma, it's already found. So you just plug in the number and going to be q 7 over 2. Of course, if you have the table, you will find 7 over 2 you will find it as a number. Okay. Now, if you need this one in terms of phi, all you have to do will be 1 minus Q7 over 2. Either way is fine. Now, part C, the probability of absolute value of x plus 3 less than 2. Okay. And we had a few examples in previous lectures on how to deal with the absolute values. And if you forgot that, you need to go back to these notes, or maybe to the math books, try to refresh your memory about how to deal with خلينا نحكي the absolute values. But for the sake of our example here, x plus 3, the absolute value of x plus 3 less than 2 is equal to x. Of course, you take the 3 to the both sides, so it will be minus 2 plus 2. You add minus 2 to the left and plus 2 to the right. So you will end up with the probability of x larger than minus 5 or less than minus 1. So x larger than minus 5, but a less than minus 2. Okay. And if we go back to the properties of CDF, of the CDFs, this probability x plus than minus 5 less than minus 2 can be written as the fx of minus 1, or the CDF of minus 1 minus the CDF of minus 5. Okay. And you can plug in, you can use the phi. Okay. Of course, in this case, x is minus 1 and x minus 5. You can represent this one in phi, but in here I solved it in terms of q. So the first one will be 1 minus q, and of course x is minus 1, and m, which is the mean, minus 3 divided by 2. The same thing for the other part. And after you do the math carefully, the end result will be 1 minus 2 minus 2q of 1. Now, if you decided to do it in phi, you just plug in phi in here. بصير بدال q هون بصير q in here q1 minus q2 minus 2 minus 1. Okay, but you still have to deal with the negative q, where you have to compare it to q function. Okay. Anyway, either way you find it, it's fine. So now these are very simple examples, but they are good representatives of what we are talking about. So make sure to understand these two terms, the phi term, the phi function, and the q function, how to deal with it, how to read the PDF right here, get the information from this PDF, the m and sigma squared. And let's go to page 41, where we have yet another example. And this example, let's read it for you. It's in front of you on the screen. It says, assume that the height of clouds above the ground at some location is a Gaussian random variable x, with mean 1830 meters, and standard deviation sigma is equal 460 meters. Find the probability that the clouds will be higher than 2,750 meters. Okay. Obviously, from this information, since we have a mean and we have we already have the mean and we already have the sigma, all we have to do, we just represent it in this notation. X, of course, this x is the height of the cloud. The random variable x is the height of the cloud, distributed normally because it's Gaussian random variable, where m, the mean, is equal 1830 is given to us, and sigma squared is the square root, or the squared of 460. Sorry. So from there, so what's needed from us is to find the probability that the random variable x, or the cloud, the clouds are larger than or higher than 2,750 meters. So from here we can change it. Of course, x larger than 2,750 is equal 1 minus the probability of x less or equal to 2,750, which is the probability, this probability right here, it's the fx or the CDF. So it's 1 minus the CDF. So in this case, you can represent it in terms of phi function. So it's going to be 1 minus phi. And of course, x in this case, 2,750, and the mean minus 1830 divided by 460. So when you do the math, it's going to be 1 minus phi 2. Now, if you go to the, obviously in our book, we have a table for phi and appendix B, and you will find it to be, this is wrong. This is 0.977. It's written here as 773. It's 0.9773. 0.9773. Okay. So in this case, it's going to be 1.9773. طبعا if you have the tables, you can read it. مثل ما حكينا موجودات in the in appendix B. So for phi 2, for 2, when phi is equal to, or x is equal to in this case, it's going to be 0.9733. So when you do the math, the probability of the clouds to be higher than 2,750 is about 2.27%. It's very low, but this is how the math is shown. Now you can do it right away in Q function. Okay, instead of going through all this, all you have to do just plug in the probability of x larger than 2,750 will be Q 2,750. You'll end up with the same result, Q2. This one is 1 minus phi 2. Now this is Q2, and again, if you go to the tables, it's going to be the same result, 2.27% or 0.0227. Okay. So this is the end of today's lecture. This is what we need to understand today. So today we covered the Gaussian random variable, or sometimes we refer to it as the mean, the normal distribution, if you will. It's a very important distribution to understand. And the only thing we covered, or we need to focus on, is how to read the PDF, how to be able to find the parameters, the mean and the standard deviation and the variance of the parameters of the PDF, and also the notation. Make sure to understand this notation. When you see it, you know exactly what it is. Also the standard normal deviation, and also the phi function, how to deal with the phi function and the Q function. And that's all I have today. Any questions? Okay, it looks like everybody is happy with what's going on as far as today's lecture. مثل ما حكينا, on Tuesday, inshallah, we will try to finish chapter 2, and hopefully, inshallah, next week we'll begin with chapter 3. So if you don't have any questions, I will talk to you on Tuesday, inshallah. يعطيكم ألف عافية. أهلين. باي باي.